Hi everyone, welcome to my channel. In this exciting journey through the world of fluid dynamics, in today's lesson, we are going to explore the fascinating phenomenon of terminal settling velocity and the renowned Stokes Law. The Stokes Law will beautifully describe the terminal settling velocity. We know that fluid dynamics is the study of how fluids, whether they are liquids or gases or vapors, will behave in different situations. One of the one of the most intriguing phenomena in this field is the motion of particles in a liquid. So, for example, if you have a fluid medium and if you have a particle, spherical particle or any non-spherical particle, how they will move and finally settle down at a certain time is what we are going to discuss. Why we should discuss this? Have you ever wondered how some tiny particles like dust in the air or the sediments in the river move through a fluid and eventually they will come to rest? It's like watching nature's own ballet and it's all governed by the laws of physics. So it's not just a random phenomena. Okay, so how much time it will take to settle down, how much time it takes to rest, all this is derived from physics fundamentals. So we should know that the settling process is not just a random occurrence, it's a highly organized and predictable event. And that's where Stokes' law comes into picture. We know that Stokes' law is a fundamental principle in fluid dynamics that allows us to understand and calculate this terminal settling velocity of particles when it navigate through a viscous fluid. So, whether you are interested in environmental science, engineering, or you are just a curious learner, this law opens up a world of knowledge. In today's lecture, we will derive Stokes' law, breaking it into step by step. We will explore how the size and the shape of the particle and also the density, viscosity of the fluid all will come together to determine the final resting place of these particles. So we are going to find out the final resting place of the particle. So if you are ever gazed at the sky and wondered why clouds seem to hang in the air or watched sand particles settle in a glass of water, we are about to uncover the scientific magic behind this all. So let's buckle up for a fascinating journey through the world of fluid dynamics where we will unravel the mysteries of Stokes' law and the terminal settling velocity. So by the end of this video, you will have a very deep understanding of the concept and how it influences countless natural and industrial processes. Before derivation of the Stokes law, let us get into some of the basic concepts involved in this derivation. We should know about because we are talking about viscous fluids here. So what is that viscous fluid? What do you mean by viscous fluid? Because the Stokes law is applicable to particles which are settling in a viscous fluid. We know what is viscous fluids. We know that viscous fluids is the one in which the fluids will be moving layer over layer. We know that, and each layer will exert a shearing force on each other. Okay, so what mean? Shearing force is exerted by one layer of fluid on another layer of fluid. If you know what is terminal settling velocity? Terminal settling velocity. So this is a constant velocity reached by the particle when the gravitational force which is pulling down the particle will equal to the resisting drag force. Terminal settling velocity is the constant velocity reached by a particle when the gravitational force pulling it downward will equal to the resisting drag force of the fluid. And at this point, the net force of the particle is zero. Net force acting on the particle is zero. So now we are talking about two forces here, gravitational force and drag force. What is this gravitational force? The force of gravity that pulls the particle downwards. The magnitude of this force depends upon mass and density of the particle. Now, what is this drag force? So, this drag force opposes the particle motion through the fluid, and this drag force depends upon the velocity, size, and shape of the particle. And also, it depends upon the properties of fluid, particularly viscosity of the fluid. And also, this drag force is defined by Stokes equation called as 3 pi mu u into characteristic length. So if it is a spherical particle, it's going to be the diameter of the particle. In this, we are going to come across even buoyant force. So we know that when a particle is submerged into a fluid, it is going to displace a volume of fluid, right? And this volume of fluid will be equal to its volume. It leads to buoyant force will oppose the gravity. So this force will be upward direction. So this is, let me say, F buoyant force means you are going to have gravity force acting downwards, and we have drag force acting upwards. Okay, so what is net force then here? Net force. So the net force means it is the force acting on the particle during terminal settling. So the net force acting on a particle during the terminal settling is difference between the gravity force and drag force. So the net force acting on the particle is going to be gravity force and drag force. So this gravity force acts downwards, this drag force acts upwards. So the difference between these two is going to be the net force, and we have seen that the net force will be zero at terminal settling velocity. And what is equilibrium condition? The equilibrium condition is when we have this gravity force equal to this drag force, we have a condition called as equilibrium. That means this particle will reach a state of equilibrium and they will descend with a constant velocity. So hereafter only you are going to have terminal settling velocity. That means it is going to settle down with a constant velocity. So at this equilibrium condition, which we are going to get a constant velocity is equal to constant, and this is termed as terminal settling velocity. Let's start deriving this equation. Now we know the basic concepts involved in this. Now we will derive the equation. So before starting the derivation of Stokes law for terminal settling velocity of a particle in a viscous fluid is going to be a spherical particle. Okay, so this is the derivation that we are going to make. So what are the assumptions? So essentially we are making some assumptions in these equations. So the assumptions made in this derivation are, one of the first assumption is here we are going to consider it as a spherical particle, because this is going to help us in making the mathematical derivation easier. So for that case, we are considering the particle to be spherical in shape. So in this spherical particle assumption, so because this derivation assumes that the settling particles are spherical in shape, it will simplify the mathematical analysis, but it limits the application to non-spherical particles. Okay. The next one is, second assumption is, we are going to assume a low Reynolds number. Low Reynolds number of particle. If, for example, in fluid flow, we had Reynolds number equal to rho Vd by mu. Okay. Whereas in case of flow through solids, we are going to have Reynolds number of the particle, which is given by rho V, diameter of the particle by mu. So here density of the fluid, viscosity of the fluid, V is the terminal settling velocity of the particle, dP is the diameter of the particle. And the third assumptions that we are making in this equation is constant properties of fluids. So we are going to assume the fluid particles to be constant. The fluid particles like viscosity, density will remain constant. Okay. Even though in real cases it will be varying with respect to temperature, pressure, and other factors. So remember what I always say: the assumptions that we are making are going to be the limitations of this law. Okay, so later we will write the same in terms of limitations of this one. So let's start with this derivation. So what we will do is we will consider a particle. Let us consider a viscous fluid, and consider a spherical particle is dropped from the top. So what we have here is a spherical particle. Remember, this type of particle moving in the fluid, it need not be a liquid. Okay, so it can be air. We have always seen dust settling in air, and we have always seen sediments are moving in the river, or even in lakes. Okay, any sediment material particles that will move across and settle down, right? So how all they will rest? When they will come to rest, it's there is a law of physics behind it, right? So that is why we are deriving this expression. Mm. So as a particle is moving across this fluid, it will come across T forces acting on it. Okay, so we are going to come across buoyant forces, drag forces, and gravitational forces, and the particle movement is governed by drag force, properties of the particle, and fluid properties. So what do you mean by this particle properties? So we know that the particle will have mass, let us say m, the particle will have a diameter, as we have assumed it to be spherical particle. The diameter of the particle is dp, and this particle will have a density, mass density of the particle, density of the particle, rho suffix p, subscript. Okay, so all the subscript p refers to particle. Similarly, we are having a fluid properties. Here, the fluid properties are density. Whenever we say density, it is mass density. Mass density, density of the fluid. F refers to fluid, P refers to particle, mass density, and viscosity of the fluid. That is mu. Let us consider the drag force. We have to consider three terms which we have designed already, discussed already in the lecture class. So the drag force is involved, and we have seen that coefficient of drag CD, this is FD. We know that coefficient of drag is involved. We have discussed this in the lecture class. Please refer to the definition. And also we come across a projected, that is projected area. What is this projected area? When you have a spherical particle and a light is flowing across it, what will be the shadow? We are not getting a spherical shadow, right? So we are going to have a circle as the projected area for spheres. Okay, it's nothing but the shadow of the particle that will be called as projected area. So three forces are acting. Three forces are acting on the particle as it is moving down. So what are the three forces acting? One is drag force, and then you have buoyant force, and you have gravitational force. Okay, so you have F gravitational force, F buoyant force, and F drag force. Okay, and we know that gravitational force, what is the direction? Gravitational force acts downwards, this buoyant force acts upwards, this drag force acts upwards. So when you make force balance according to Newton's law, the net force in your direction is equal to mass into acceleration into the direction. So we have Fg minus Fb minus Fd is equal to mass into acceleration. Okay, so this is the force balance that we are making, and by definition we have seen in our lecture class, we have CD equal to, it's defined as the ratio of drag force by projected area to the product of density into velocity head. Okay, so this is the definitions that we are having. Okay, so if you rearrange it, what we have is, let it be equation number 1. If we rearrange this, what we have is, from definition of CD, this is by definition. Okay, so from definition you can rearrange what is FD. FD is equal to half CD rho u square into AP. Let it be equation number 2. And we know that by definition of gravity, gravitational force equal to m into g. Okay, and let it be equation number 3. And what is buoyant force? Buoyant force is equal to mass of the fluid displaced into g. Let it be equation number 4. What is mf? F refers to the fluid, so mass of the fluid displaced, where mf is mass of fluid displaced. Remember, by Archimedes principle, we know that volume of fluid displaced is equal to volume of the particle. So volume, we know the density equal to mass per unit volume. So we can express the volume equal to mass by density, right? Volume equal to mass by density. So here you can write mass of the fluid divided by density of the fluid is equal to mass of the particle divided by density of the particle. Or we can say that mf equal to rho by rho p into m. Let it be equation number 5. I repeat, volume of the fluid displaced is equal to volume of the particle. So we can write mass density is ratio of mass per unit volume, rearranging volume equal to mass by density. So this side also we are writing volume in terms of mass by density of the fluid. So mass of the fluid by density of the fluid. Right hand side volume of the particle is mass of the particle by density of the particle. Rearranging, we write mass of the fluid equal to rho by rho p into m, equation number 5. Okay. We can substitute this 5 in 4. So substituting 5 in 4, so what we have is buoyant force equal to, instead of m of g, we are writing this replaced by rho p into mass of the particle into g. Let it be equation number 6. Similarly, what is acceleration in the direction? Acceleration is equal to du by dt. So let it be equation number 7. So we will substitute 2, 3, 6 and 7 in the net force balance equation number 1. So what we will get is mg minus, that is the gravity force, minus this is buoyant force rho by rho p into mg minus drag force, that is half c drag rho u square ap. Okay, so these are the three forces in the left hand side, and the right hand side is mass into acceleration. We write du by dt. That is from equation number 7. Okay, so what we can do here, we have mg common. So mg can be written mg into 1 minus rho by rho p minus half cd rho u square ap is equal to m into du by dt. Okay, this is equation number 8. So now we have almost reached to substitute the necessary conditions involved here. So we know that when at terminal settling, that is at terminal settling velocity, as per definition, you get u tends to ut, that is 1. So we have acceleration tending to 0 because this velocity is constant, right? So we have defined what is terminal settling velocity. It's a constant velocity reached by the particle when the gravitational force pulling it downward equals to the resisting drag force of the fluid. At this point, the net force of the particle is 0. So that is the condition and definition for terminal settling velocity. Substituting that condition, what we are going to have is we are replacing this u with u subscript t. T refers to terminal settling velocity. Okay. So what we have is mg into we have mg into 1 minus rho by rho p minus of cd rho. Here subscript is t. Okay, ut square ap equal to 0. Remember, acceleration is 0. So this term becomes 0, right hand side becomes 0, which means that we have a condition where this equal to this. Okay, so we can write that mg into 1 minus rho by rho p is equal to half cd rho ut square ap. Okay, so this equation we have, let it be equation number 9. Okay, okay, we have, and it is a gravity settling. G is constant. We know that in gravity settling, G is constant. Acceleration will decrease with time and approaches to 0, and a constant value of velocity, terminal settling velocity, is achieved. So what is the volume of the particle here? So we can replace some of the terms here because mass is involved. So we can replace mass in terms of diameter of the particle, and also we can make use of the definition of drag force here. Okay, so what we will do, we'll use some mathematics. That is the volume of the particle. What is the volume of the particle? Volume of the spherical particle is, what is the volume of the particle? 4 by 3 pi r cube, right? So 4 by 3 pi r cube is the volume for a sphere. So we can write it in terms of diameter. That is 4 by 3 pi d cube by 2 power 3 8. So that is equal to 1 by 6 pi d cube. Okay. So what is mass then? Mass of the particle is, what is the mass of the particle? So volume is known. So we can write, we know the density of the particle. So we know mass per unit volume is density. We have volume of the particle. Okay. So we can write mass of the particle equal to density of the particle into volume of the particle, which is equal to, we have V is this, right? We have pi by 6 dp cube. In general formula, I am writing for particle. Okay, pi by 6 dp cube into rho p. Let it be equation number 10. Mass of the particle. And what is projected area for this? Pi d square by 4. As I said, even though it is a spherical particle, projected area is just a circle. It's like shadow. When a light is passing, you cannot see sphere here, right? So you see a circle here. So that is called projected area. You have AP equal to this much. Also, from Stokes law, we have drag force given by, there is another law which defines this drag force, but we are using the Stokes approach. So we use the definition given by them. So drag force equal to 3 pi mu ut into diameter of the particle. This is again by definition. There is another law called Einstein approach. So they define differently. So here we use Stokes definition. We have this equation. Okay. So we have definition of FD here, AP here. So we can substitute that in the equation, right? Can we substitute that? So that's, we are going to complete the derivation here now. So we have by definition CD equal to FD by AP rho into ut square by 2 here in this case. Okay, u generally is u, but here we are talking about terminal settling velocity. So we have this expression. So we can show here something, that is FD by AP. FD is from 12, equation number 11, 12. Okay, from 11 and 12, what we have is 3 pi mu u dp divided by pi dp square by 4 divided by rho into ut square by 2. If you simplify, what you will get is, you have this pi getting cancelled, dp getting cancelled. So you have this t here. So here also power getting cancelled. So what we have is 4 2s are 8, 8 3s are 24. So you have 24 mu divided by this rho is there left, mu was left, and denominator you have ut left, and in the denominator we have dp also left. So this is nothing but 24 by ni of the particle. So this is where we are defining Reynolds number of the particle, where Reynolds number of the particle is equal to rho ut diameter of the particle divided by mu of the fluid. Okay, we have drag c drag equal to this. Okay, let it be equation number 13. So what we are going to do is we are going to get a final equation once we substitute this 10, 13 and 11. So when you substitute 10, 11 and 13, we are going to get in 8. So we substitute that in our equation number is that 8 or 9. Substituting this in equation number 9, so what we will have is, these are 9 equation, again I am writing because we are away from it. So mg into 1 minus rho by rho p is equal to half rho ut square cd into ap. Okay, so here we are going to substitute what is cd, what is ap, and what is m. Okay, so what is m? M is 5 by 6 rho p.
dp cube.
Okay, dp cube actually, into, as usual in the equation we have 1 g into 1 minus rho by rho p equal to half into rho ut square, and for cd we have 24 mu by rho ut dp, and for this projected area we have 5 by 4 dp square. Okay, can we simplify this now? Once, so you cancel out the terms. Okay, so here also you have rho 1 minus rho by rho p is there. Okay, so here rho is there, here rho p is there, so this rho p will get cancelled. Okay, so we have rho p minus rho here, so what you will cancel out? So simplification will give you the right hand side. If I keep ut, the right hand side, this dp square will stay back, g will stay back, rho p minus rho will stay back, and we are going to have 18 mu. Okay, please check what we are doing here. Here you have 6, 2, 4, 24. So they all will get cancelled to become 18. So you have this rho p, this 1 minus rho by rho p, we can write like rho p minus rho by rho p. So this rho p will get cancelled, pi will get cancelled. Okay, dp square is there, left hand side, and right hand side also dp square is there, dp cube actually. So from equation 10, what we have is dp cube, that correction please note. So the dp cube is there. So you are going to have dp, it get cancelled. This denominator dp and numerator dp will get cancelled. So one more dp will get cancelled here. So we have dp square finally. Okay. So dp square will come. This g term will come. Rho p minus rho will be coming. So remaining is ut square. This ut square is there. Denominator ut is there. So here also will become ut. Okay. And you have this density getting cancelled here. So this mu is left, so that mu will moving out to left hand side of the equation. So we have final expression for this one, ut equal to dp square rho p minus rho into g divided by 18 mu as the final equation. And we classify this equation is called as terminal settling velocity. Stokes law for this equation is called as Stokes law for terminal settling velocity of a particle in a viscous fluid given by dp square into rho p minus rho into g divided by 18 mu. Okay. Now, as we have made some assumptions in this equation, this has some limitations, right? So what are the limitations of this equation? Number one is it is only applicable to spherical particles. But in real life scenarios, we are going to have particles like non-spherical particles. So it doesn't take into account of shape of different particles other than spherical particles. So this is only applicable to spherical particles. That is one of the limitations. And the second limitation is in the assumptions we have made it, it's applicable for low Reynolds number, particularly when Reynolds number of the particle is less than 0.1. Okay. That is why this even this Stokes flow is also called as low Reynolds number flow. Okay. So this because of this limitation, this is not applicable to high Reynolds number fluids, and turbulent flow fluids, turbulent flows. So these are the limitation. I repeat, this fluid, the limitations are the Stokes law for terminal settling velocity of a particle in a viscous fluid is applicable only for spherical particles. It's only applicable for Reynolds number, so it doesn't take into account of non-spherical particles. It is not applicable for high Reynolds number and turbulent flow, and also it assumes constant fluid properties. But whereas in real situations, as it's told during the assumptions, due to temperature and pressure variations and other reasons, the fluid properties may change. Okay, so these are some of the limitations. However, this equation is very much useful in various applications. So let us list out some of the applications of this Stokes law for terminal settling velocity. So this is particularly very much useful in water treatments and wastewater treatments. Because you know that we have several, I think even in mechanical operation course, you might be learning about several sedimentation tanks. We have clarifiers. So all these designs and optimizations and improving the efficiency needs the application or understanding of the Stokes law for terminal settling velocities. Also, they are used in various chemical industries like processes like unit operations like separations and filtrations. These particles, how much time a particle will take to settle down is important in designing those equipments. Also in pharmaceutical industries, so how much time this particle, what is the settling time? Because we prepare several medicines in the form of suspensions, right? So, so the understanding of terminal settling velocities is important to determine the quality and consistency of the suspensions made prepared. Okay, So not only in this pharmaceutical industry, if you look at the big large scale, so we have geotechnical in geotechnical engineering applications, in soil mechanics, even for erosion control, this Stokes Law finds applications. And if you look at petrochemical engineering, petroleum industries, in petroleum engineering, particularly we discuss about drilling muds. Drilling muds are like lubricants being added when you are doing exploration. Drilling is being done. So the settling of particles in the drilling mud, design of settling tanks for the separation of oil, solids. Okay, so in the production units, so this Stokes law finds applications. Also in aerodynamics, aerospace and aviations, particulate separation systems for aircraft engines, spacecraft propulsion systems. This Stokes law is being used. So as I said, even in civil and environmental science, particularly the sediment transportation, erosion, how the sediments are getting deposited in rivers and lakes, and particularly in coastal environments. This Stokes law for external setting velocity finds useful. For Reynolds number of the particle greater than zero point 0.1, so we have other empirical equations available. For example, we have a Newton's law for terminal settling velocity determination, which gives this terminal settling velocity is equal to 1.75 into square root of g into rho p minus rho into diameter of the particle divided by density of the fluid. Rho refers to density of the fluid. P refers to particle. Okay. So this equation is applicable for higher Reynolds number. And we have another empirical equation which is called as Schiller Ormond, which states this terminal settling velocity is equal to 1 by 18 into diameter of the particle square by mu into rho p minus rho by rho f, that is rho density of the fluid, plus 2.65 diameter mu. Okay, so we have two equations. These two equations Actually, how they are derived? So first we do dimensional analysis, and through experiments, this constant value is determined. So this way, there are other equations which can be utilized to determine the terminal settling velocity of a particle in a viscous fluid. Now let us solve some numericals. What is the final equation that we are having? We have terminal settling velocity equal to denominator is 18 mu dp square rho p minus rho into g. Okay, so this is a Stokes law for terminal settling velocity. Terminal settling velocity. Okay, so now we can do some numericals. Question is first one. Questions are similar. Okay, so I'm just going to do some straightforward numericals. Calculate the terminal settling velocity. Calculate the terminal settling velocity of a glass bead which has a diameter of 0.1 mm and density 2500 kg per meter cube. Remember, it can be given as specific gravity equal to 2.5, right? So density of the particle is given. And determine. Okay, so we are calculate the terminal settling velocity of a glass bead with a diameter 0.1 mm and density 2500 kg per meter cube in water. We know the density of water is 1000 kg per meter cube. Viscosity 0.001 Pascal second. Okay, so what is how to solve this? So we have this equation, the straightforward equation. Diameter of the particle is given, but you have to substitute in this one. So how to solve it? First, let us write the given data in SI units. Diameter of the particle is given, zero point 0.1 into 10 power minus 3 meters. Density of the particle is given, 2500. Density of the fluid is 1000 all kg per meter cube. G value we know 9.81 into meter per second square. Viscosity is given 0.001 kg per meter second. That is Pascal second. Okay. So all four parameters are known. We can substitute to get UT value. UT is diameter, that is 0.1 into 10 power minus 3 into 9.81 into 2500 minus 1000 divided by 18 into 0.001. Substitute with the units, we will get in meter per second. Kindly comment your answers. Getting around in between 5.5 to 6 into 10 power minus 3. Okay, please comment your answer if you are watching this video. Second question. So now question statement is going to be same. Okay, so I am just going to give set of particles and the fluid. All question is to determine terminal settling velocity, that is UT determination problems. Okay, so consider a steel ball with a diameter 0.02 mm, so 0.02 meters, and density 7850 kg per meter cube, and the fluid is vegetable oil. with viscosity 0.1 Pascal second, density 920 kg per meter cube. Again, we will get UT value in meter per second. Okay, direct substitution. It's another numerical. Consider again what you are doing, calculating terminal settling velocity, that is UT. Determine UT. Here the particle is lead pellet with the density 11,340, diameter of the particle 0.005 meters, and the fluid here is ethanol. Its density 789 kg per meter cube. Viscosity, you can take that of water, that is 0.001 Pascal second. We are going to get UT in terms of meter per second. Fourth one, again find out TSV, thermal settling velocity, that is UT for the particle plastic bead with the diameter 0.03 mm. Density of the particle 900 kg per meter cube, and the fluid is honey with the density 1400 kg per meter cube, viscosity 2 Pascal second. We will get UT in terms of meter per second. And the particle is gold nugget, and the fluid is mercury. The particle diameter is 0.002 meters. Density of the particle 19,320 kg per meter cube, and the fluid has a viscosity of 0.001 Pascal second and density of 13,600 kg per meter cube. We are going to report UT value in terms of meter per second. So these are simple numericals. So you should be ready to solve numericals because the equation is Stokes law is not just an abstract concept. We have understood that it has real world applications in fields like environmental science, engineering, and industrial processes. So we have even explored the practical applications to get a sense of why this law matters to us. As we wrap up, now you have a deep understanding of Stokes' law and how it influences countless natural and industrial processes. But remember, this is just the beginning of our journey into fluid dynamics. There is a world of fascinating science waiting for us to explore. Thank you so much for joining my classroom. Meet you in another lecture. Bye bye.